Somewhere near the edge of the observable universe, hidden behind a wall of closer galaxies, there is an object that should not exist, not because it is strange, not because it is dangerous, not because it is doing anything unusual. It should not exist because, according to everything we thought we understood about how the cosmos assembled itself, there was not enough time for it to be there. When the James Webb Space Telescope turned toward the first few 100 million years of cosmic history, it was expected to find the beginning. Small galaxies, faint, disorganized clumps of gas, the rough draft of a universe still figuring out how to make structure. Instead, it found something already finished. A black hole so massive and so early that it does not fit inside the timeline of the universe. And here is the part that keeps astronomers awake at night. The more carefully they measure it, the worse the problem gets. To understand why this is a crisis and not just a curiosity, you first have to understand the rule that it breaks. A black hole is not supposed to be born large. In the standard story of the cosmos, the very first black holes began as seeds. When the earliest generation of giant stars ran out of fuel and collapsed under their own weight, they left behind dense cores weighing perhaps a few hundred times the mass of our Sun. Small, by cosmic standards, almost trivial. From there, a black hole grows the only way it can. It feeds. It pulls in surrounding gas, that gas spirals inward, friction heats it to millions of degrees, and the black hole slowly, patiently gains weight. But there is a speed limit on that feeding, and it is not a suggestion. It is built into physics itself. As gas falls inward, it glows so violently that the outward pressure of its own radiation begins to shove away the next meal. The harder a black hole tries to eat, the more fiercely it pushes its food away. Astronomers call this the Eddington limit, and for decades it has acted like a governor on an engine. A black hole can only pack on mass so quickly before it chokes on its own light. So, now do the arithmetic. Start with a seed of a few hundred suns, feed it at the fastest rate that physics normally allows, without interruption, without a single pause. To reach the scale of the monsters sitting at the centers of galaxies today, you need billions of years of uninterrupted growth. The early universe did not have billions of years to give. The object that broke this story open has a plain, forgettable name. Astronomers call it UHZ1. Finding it required a trick borrowed from nature, a massive foreground cluster of galaxies known as Abell 2744, sometimes nicknamed Pandora's cluster, sits between us and the deep universe. Its gravity is so immense that it bends the fabric of space around it, warping and magnifying the light of everything unlucky enough to be directly behind it. The cluster becomes an accidental lens, a telescope the size of a galaxy cluster, built by gravity, pointed at the dawn of time. Peering through that lens, the James Webb Space Telescope caught a faint smudge of infrared light, and NASA's Chandra X-ray Observatory, staring at the exact same patch of sky for more than 2 weeks, caught something else. X-rays, the unmistakable glow of superheated gas being torn apart as it falls into a black hole. 2 telescopes, 2 completely different kinds of light. One object. That X-ray signal was so faint that Chandra should never have seen it at all. It was only detectable because the gravitational lens amplified the light by roughly 400%. Without that cosmic accident, this discovery does not happen. We simply never know it is there. When they measured the distance, the answer was staggering. The light from UHZ1 left its galaxy roughly 470 million years after the Big Bang. It has been traveling for more than 13 billion years to reach us, crossing a distance of about 13.2 billion light-years. We are seeing this galaxy when the universe was only 3% of its current age. Understand what that means. We are not looking at this galaxy as it is now. We have no idea what it is now. We are looking at a photograph of the universe's infancy, delivered 13 billion years late. And then they weighed it. The estimates place the black hole at somewhere between 10 million and 100 million times the mass of our Sun. Not a seed, not a stellar remnant, a fully grown supermassive black hole, already feeding, already enormous, when the universe was still learning how to make its first light. But raw size is not what makes this a genuine problem. The problem is the ratio. In the universe around us today, there is a remarkably stable relationship between a galaxy and the black hole at its heart. Add up every star in a typical galaxy, and their combined mass is roughly 1,000 times greater than the black hole they all orbit. The black hole is a rounding error, 1/10 of 1%. It is the seed buried deep inside the fruit. In UHZ1, that relationship collapses entirely. The black hole is not a rounding error. Its mass is roughly comparable to every single star in the galaxy combined. It is as though the seed had grown as heavy as the entire fruit surrounding it. This is why astronomers reached for a blunt, almost uncomfortable label. They call these objects overmassive black holes. Black holes that are simply too big for the galaxies that contain them. And then they weighed it. And if UHZ1 were the only one, this would be a footnote, an oddity, a single strange object in a universe full of strange objects. It is not the only one. As the James Webb Space Telescope kept scanning the young universe, it kept finding them. A whole population of faint, tiny, deeply red points of light, so small and so uniformly crimson that astronomers nicknamed them the little red dots. Look closely at these dots, and many of them appear to conceal a heavy black hole at their center, far heavier than their host galaxy should be capable of explaining. In the most extreme cases, the numbers stop sounding like measurements and start sounding like mistakes. Instead of the black hole representing 1/10 of 1% of its galaxy, it makes up 10%, 20%, in some cases 30% of the entire mass. And in a handful of the strangest little red dots, the black hole at the center appears to outweigh every star in its galaxy put together. One more object drives the point home with brutal clarity. A brilliant quasar catalogued as J0313-1806, shining out from roughly 670 million years after the Big Bang, is powered by a black hole exceeding 1.6 billion times the mass of the Sun. More than 1 billion suns, fully assembled in a universe that had barely begun. So the question is no longer whether a single black hole somehow grew too fast. The question is how an entire generation of them did it simultaneously. There are a few ways out of this, and every one of them rewrites part of the story of how the universe was built. The leading explanation is that these black holes never began as small seeds at all. Instead of waiting for a star to be born, live out its life, and die, an enormous cloud of primordial gas may have collapsed directly into a black hole in a single catastrophic event. No stellar stage, no waiting, not a few hundred suns to begin with, but a heavy seed weighing 10,000 to 100,000 suns, created almost instantly. Astronomers call this direct collapse. It was proposed as theory years before anyone saw evidence for it, and UHZ1, with its unusual X-ray signature, its extreme distance, and its overgrown central black hole, matches the theoretical fingerprint of exactly this kind of birth with uncomfortable precision. It may be the first real observational evidence that heavy seeds are how the universe manufactured its earliest giants. The second possibility is that the speed limit is not really a limit. In the dense, chaotic, gas-drenched hearts of the first galaxies, a black hole might have fed far faster than the Eddington rate allows, gorging in violent bursts, temporarily overwhelming its own radiation and racing ahead of the clock. But there is a third possibility, and it is the one that turns this from a settled discovery into a live scientific argument still being fought right now. We cannot see these black holes. Not directly, not even close. We infer their masses indirectly from the light of the gas swirling around them and from how fast that gas appears to be moving. Every one of those measurements depends on assumptions, and every assumption has to survive a journey of 13 billion years. In the past year, several research teams have begun to question whether those measurements can be trusted at this distance at all. They argue that at least some of these overmassive black holes may not be nearly as heavy as they first appeared, that the methods we use to weigh a black hole across the width of the observable universe may be systematically fooling us, that once the observational biases are stripped away, the population might look far more ordinary than the headlines suggested. In other words, either the universe is broken or our ruler is bent. And right now, astronomers genuinely do not agree on which. That uncertainty is exactly what makes UHZ one more than a record on a list. Because if these black holes are real, if the measurements hold, then the order of creation may be reversed from everything we assumed. We pictured galaxies forming first, gathering their gas and stars, with black holes growing up slowly inside them like something raised by a parent. But an overmassive black hole hints at the opposite arrangement entirely, that the black hole came first, that the galaxy assembled itself around the darkness at its center, the seed, in a sense, growing the fruit. 13 billion years ago, in a universe that had barely learned how to make light, something in the dark was already enormous. We found its shadow by accident, bent and magnified through the gravity of another galaxy cluster, at the absolute limit of what our instruments can detect. And after all of that, we still cannot fully explain how it got there. The James Webb Space Telescope was built to show us the beginning. Instead, it may have shown us that we never understood the beginning at all. The dark is still full of things we cannot explain. Subscribe, and we'll find the next one together.